The most common planet in the Milky Way is one you have never seen, one no human has ever seen, because there are none of them anywhere near us. They are called super-Earths, bigger than our world, smaller than Neptune, and according to every major telescope survey we have run in the last 2 decades, they orbit the majority of stars in the galaxy, not a slim majority, a commanding one. When researchers finished processing the data from the Kepler Space Telescope, the number that came back was staggering. Roughly 77% of Sun-like stars appear to host at least one planet in this size range. Around smaller, cooler red dwarf stars, the numbers climb even higher. Some estimates put the occurrence rate above 1 super-Earth per star. There are hundreds of billions of stars in the Milky Way. The arithmetic from there is not complicated. And yet, look at our own solar system. 8 planets, 4 rocky worlds close to the Sun, 4 giants farther out, and in that entire lineup, not a single super-Earth, not one. The size category that dominates the galaxy does not appear once in the system we live in. Mercury is too small, Mars is too small, Venus and Earth come closest, and they still fall well below the lower threshold of what qualifies. Whatever process fills the inner orbits of other stars with these worlds, something different happened here. This is one of the stranger puzzles in modern planetary science. Not strange in the way that distant or abstract problems can feel strange, but strange in the way that demands an answer. We used our own solar system as the template for how planets form. For decades, it was the only system we had. The models were built around it, the textbooks were written from it. Then we pointed telescopes at other stars and discovered that almost everything we had assumed about what a typical planetary system looks like was wrong. The most common outcome of planet formation, repeated around star after star across the entire galaxy, is a type of world our own Sun never produced. If you find comfort in these gentle explorations of space and science, I'd be grateful if you'd consider subscribing and giving this video a like. I'd love to know where you're watching from and what time it is for you. Feel free to drop your location and time in the comments below. Were we watching a system that formed wrong? Or were we the exception that survived precisely because of how it formed? That question has a real answer, and it is not a comfortable one for anyone who assumed our solar system was a reasonable cosmic average. What makes this paradox genuinely unsettling is the scale of it. This is not a matter of our solar system being slightly unusual. The inner region of our solar system, the zone inside Earth's orbit where super-Earths pile up around other stars in chains of close, tight orbits, is almost empty. Mercury sits there, barely, with a mass roughly 5% of Earth's. The region that statistics say should be the busiest, most densely packed part of any planetary system is, in ours, nearly barren. Something happened in the early solar system that cleared that space, or prevented it from ever filling up. Maybe both. The answer, as it turns out, involves the structure of the disk of gas and dust the Sun was born in, the catastrophically fast formation of Jupiter, and a period of planetary migration so violent it may have erased an entire first generation of worlds. None of these explanations is simple. None of them is fully settled, but together they are beginning to tell a coherent story about why this solar system produced Earth instead of a stack of super-Earths, and what that difference means. To understand why they are everywhere except here, you have to go back to the very beginning, to the cloud of gas and dust that became our solar system, and ask what happened differently. Before the first exoplanet surveys came back with results, almost nobody expected planets like this to exist at all. The models of planetary formation that astronomers were working with in the late 20th century were built almost entirely on what existed in our own solar system. Rocky planets on the inside, gas giants further out, a clean progression from small and dense to large and diffuse. Nobody had a strong reason to predict an entirely separate category sitting between those two zones. This was because in our system, that zone is empty. There is nothing between Mars and Neptune. No planet occupies the size range from 1 to 2.5 Earth radii. It simply does not exist here. So when the surveys started coming back, that size range turned out to be the most populated region in the entire exoplanet catalogue. Astronomers had to rethink something fundamental. The term super-Earth is a little misleading and scientists know it. What the name actually describes is a size category, not a type of world. A super-Earth is any planet with a mass roughly between 1 and 10 times Earth's mass, and a radius somewhere between 1 and 2.5 Earth radii. That is a wide range. At the smaller end, you have planets not dramatically different from Earth in size. At the upper end, you have worlds that may be almost entirely ocean, or wrapped in atmospheres so thick you would never see the surface from above. The name implies something familiar, a bigger version of home. In reality, Super-Earth is more of a filing system than a description. It tells you what a planet is not. It is not a gas giant, not a Neptune, not an Earth, more than it tells you what it actually is. If you were somehow able to stand on one of the denser, more massive super-Earths, the first thing you would notice is the gravity. A planet twice Earth's mass, but slightly more compact, would have surface gravity substantially heavier than what we experience. Your body would weigh more. Moving would feel like effort. Jumping would be disappointing. That alone would make the experience profoundly different from anything humans are adapted for. The atmosphere above you, assuming the planet had one, would likely be thicker. Gravity holds gas in place more effectively. Larger rocky planets tend to outgas more material during their formation and geological history. Whether that atmosphere would be breathable or even survivable depends entirely on the specific chemistry involved. That varies enormously from system to system. Then there are the water worlds. Some super-Earths appear to be mostly water ice and liquid, with densities far lower than what you would expect from a pure rock and iron composition. These are not Earth-like in any practical sense. There is no crust to stand on, no tectonic activity in the familiar sense. The pressure at depth would be extraordinary, potentially creating exotic forms of ice that do not exist on Earth, even at the bottom of a planet-wide ocean. Calling these worlds super-Earths is technically accurate by the mass and radius definition, but the mental image the name conjures, a planet somewhat like ours, just bigger, is almost entirely wrong. What caught astronomers off guard was not just the existence of super-Earths, but the sheer variety hiding inside that one category. Within the size range from 1 to 2.5 Earth radii, you have rocky worlds, ocean worlds, planets with thick hydrogen envelopes, stripped cores of what were once larger planets. The same label covers wildly different objects, which is part of why understanding super-Earths has been difficult. You cannot treat them as a uniform class. They are a size bin, not a physical type. The radius tells you roughly how big they are. It does not tell you what they are made of, how they formed, whether they have magnetic fields, whether their interiors are still active, or whether anything resembling life could persist on their surface. Part of what makes the absence of super-Earths in our solar system so strange is that they appear to be the natural outcome of planet formation almost everywhere else. The core accretion process, where rocky embryos gather material through repeated collisions over millions of years, seems to reliably produce planets in this size range when the ingredients are available. You would expect our system to have at least one. The fact that it has none, while most other systems have several, suggests something actively prevented their formation here, or destroyed them after they formed. That is not a small puzzle. That is the central question. There is also a curious feature in the size distribution of these planets that hints at deeper physics. When you plot the radii of all observed super-Earths and mini-Neptunes, you do not get a smooth bell curve. You get two separate peaks with a gap in between. Planets around 1.5 Earth radii are common. Planets around 2.5 Earth radii are common. Planets right in between, around 1.8 Earth radii, are surprisingly rare. Something is carving a gap in the population. Whether that is related to formation processes or to the gradual stripping of atmospheres by stellar radiation is still being worked out. But the gap itself tells you the universe's preferences about what size a small planet should be. The two answers it keeps giving are different from the four answers our solar system gave. By the time surveys had catalogued thousands of these worlds, the shift in perspective was complete. Our solar system had always been treated as the reference point, the baseline, the standard version of what a planetary system looks like. The exoplanet surveys did not just add data points, they overturned the assumption. The most common planetary outcome in the galaxy, the type of planet that orbits the majority of stars, is one that our entire solar system somehow failed to produce even once. The surprise was not just that super-Earths existed, it was that they seemed to be everywhere. That our solar system, the one we had been using as the template for how planets form, was the strange one. When the Kepler Space Telescope finished its primary mission and the statistics came back, the number that stopped people cold was 77%. Not 7%, not 17%. 77% of Sun-like stars in the Kepler survey appeared to host at least one planet in the super-Earth size range, with an orbital period under 300 days. That means that when you look up at a Sun-like star on a clear night, the odds are better than even that a super-Earth is already there, circling in the dark, invisible and unvisited. That number sat in the astronomical community like a stone dropped in still water. Ripples went outward and did not stop. Before Kepler, planetary scientists had built their understanding of how solar systems form largely from the one example they had. Our system. 8 planets, 4 of them rocky and small, 4 of them giant and gassy, arranged in a rough order that made a kind of sense. Smaller worlds inside, giants outside. The model was tidy. Then Kepler started returning data and the model started breaking. What the telescope kept finding, over and over, in system after system, was planets jammed in close to their stars in size ranges our solar system simply does not contain. The 77% figure was the sharpest expression of a pattern that had been building for years. But that number applies specifically to Sun-like stars, which astronomers call G-type stars. Move to slightly cooler, slightly smaller K-type stars, and the occurrence rate climbs higher. Studies estimate that K-dwarfs host roughly 125 super-Earths per 1,000 stars. Move further to the most common stars in the galaxy, the red dwarf M-dwarfs, and the numbers become almost difficult to process. Some estimates place the super-Earth occurrence rate for M-dwarfs above 350 per 1,000 stars. more than one super-Earth per star. Around some classes of red dwarfs, the rate is high enough that hosting multiple super-Earths appears to be the default outcome rather than the exception. The galaxy did not build one of these things as a curiosity. It built them wholesale. Here is a way to feel the weight of that. There are roughly 100 billion stars in the Milky Way. A conservative estimate suggests that somewhere between 1/4 and 1/2 of those stars are M dwarfs alone. If each M dwarf hosts even a single super-Earth on average, you are looking at tens of billions of super-Earths just from that one stellar category. Add the contributions from G dwarfs, K dwarfs, F-type stars, and the number you arrive at is somewhere in the hundreds of billions. Hundreds of billions of planets in a size range that includes 0 representatives in our own solar system. The absence here is not a small gap in the record. It is an enormous silence against an extraordinary amount of noise. What makes the numbers stranger is where these planets tend to sit. The super-Earths Kepler found were not hanging out in the outer reaches of their systems. They were packed in close. Most of the detected super-Earths orbit their stars in periods of days to weeks, not years. In our solar system, the region inside the orbit of Mercury sits essentially empty. A little rock, some dust, nothing of substance. In the majority of planetary systems we have examined, that same region is occupied, sometimes heavily occupied. Multiple super-Earths orbiting shoulder to shoulder in the inner zone, completing full orbits in the time it takes Earth to finish a season. The comparison is not subtle. The Kepler data also revealed something about the structure of these inner systems that added another layer of strangeness. In many cases, the super-Earths were not scattered randomly around their stars. They appeared in chains, orbiting in ratios that hinted at gravitational coordination. 3 planets completing 2, 3, and 4 orbits respectively in the time a 4th completes 1. These resonance chains are the signature of migration, of planets that moved inward through the disk and piled up against each other. They are not accidents. They are the record of a formation process that operates with a kind of regularity across wildly different stellar systems. Around M dwarf specifically, the occurrence rates in the habitable zone are striking. One long-term survey estimated that roughly 41% of nearby red dwarfs host a super-Earth within the orbital range, where liquid water could theoretically exist on a rocky surface. That number, if anything, is probably conservative. Detection methods that work well for close-in planets become less reliable at slightly wider orbits, meaning the census is almost certainly incomplete. The real rate could be higher. The point is that these planets are not a fringe outcome of planetary formation. They are what planetary formation does, most of the time, around most stars. And yet, our Sun is a G-type star. It falls squarely in the category where 77% of stars appear to have super-Earths. The odds were in favor of our solar system having them. The priors said they should be here, crowded inside the orbit of Mercury or Venus, completing dozens of orbits per year, solid and massive, and entirely absent from every observation ever made from this planet. No instrument has ever detected a super-Earth around our Sun, because there are none to detect. The 4 rocky planets we have are low mass, spread out, and orbiting in the outer portion of the zone where most systems concentrate their inner planets. We are in a statistical minority so clear that understanding why has become one of the defining questions in modern planetary science. The sheer weight of the numbers points in one direction. Something specific and probably unusual happened in our solar system. Not a small deviation from the norm, a complete departure from what the galaxy does with its stars and their surrounding material, most of the time, in most places. Whatever produced our solar system's inner emptiness, the rest of the galaxy did not get the memo. There is a simple reason we knew almost nothing about super-Earths before 1995. We had no way of finding planets around other stars at all. The night sky had been studied for thousands of years, and the existence of other planetary systems was widely assumed, but assumption is not detection. Stars are so bright and planets so dim that even our best instruments could not separate one from the other across interstellar distances. A planet next to its star is like a firefly next to a lighthouse, seen from miles away. You do not see the firefly, you only see the light. The first confirmed exoplanet around a Sun-like star was detected in 1995 using a technique called radial velocity, sometimes called the Doppler method. The logic behind it is elegant. A planet does not simply orbit its star, both the planet and the star orbit their shared center of mass. When a massive planet pulls its star toward us, the star's light shifts very slightly toward the blue end of the spectrum. When the planet pulls the star away, the light shifts toward the red. By measuring these tiny shifts in a star's spectrum over months or years, astronomers can infer the presence of a planet without ever seeing it directly. The signal is almost impossibly faint. Detecting Jupiter's influence on our own Sun from another star would require measuring a velocity change of about 12 meters per second. Detecting Earth's influence would require measuring less than 1/10 of a meter per second. The instruments of the early 1990s were nowhere near that sensitive. What radial velocity could find in those first years were massive planets, gas giants the size of Jupiter or larger, pulling their stars with enough force to leave a measurable signal. That first confirmed planet, 51 Pegasi b, was a Jupiter mass world orbiting its star in just 4 days. Nobody had predicted that something like it was possible. Through the late 1990s and into the 2000s, radial velocity surveys slowly extended the catalogue. By around 2009, a few hundred exoplanets had been confirmed. Super-Earths appeared occasionally in the data, but they were hard to detect. The gravitational tug of a planet 5 or 6 times Earth's mass is real, but subtle. Catching it required years of careful observation on the same star. Progress was slow. The catalogue was a trickle. Then Kepler changed everything. NASA's Kepler Space Telescope launched in March 2009 and stared at a single patch of sky containing roughly 150,000 stars. It was looking for transits. The transit method works on a different principle than radial velocity. When a planet's orbit carries it directly between its star and Earth, the planet blocks a small fraction of the star's light. The star dims slightly, briefly, then brightens again as the planet moves past. For an Earth-sized planet transiting a Sun-like star, the dimming is about 0.01%. For a super-Earth, slightly more. Kepler measured stellar brightness with a precision that had never been achieved from the ground, and it did so continuously, watching the same stars day after day for years. If a planet transited once, Kepler waited for it to come around again, and again. 3 transits with consistent timing and depth were enough to flag a candidate. The numbers that came out of Kepler were staggering. Within a few years, the mission had identified thousands of planetary candidates. Confirmation required follow-up, often with radial velocity measurements to verify that the dimming signal was really a planet and not a binary star or an instrumental artifact, but the sheer volume of candidates made clear that planets were not rare. They were everywhere. And the candidates that kept appearing in the data over and over in system after system were not gas giants. They were small planets, massing somewhere between Earth and Neptune in orbits ranging from a few days to a few hundred days. Super-Earths and mini-Neptunes dominated the catalogue from the beginning, and they never stopped dominating it. By the time Kepler's primary mission ended in 2018, the confirmed exoplanet count had grown past 3,800. A successor mission called TESS, the Transiting Exoplanet Survey satellite, launched that same year and began mapping the rest of the sky that Kepler had missed. Where Kepler stared at one region, TESS scanned the entire sky in sectors, focusing on the closest and brightest stars. By 2024, the total count of confirmed exoplanets had crossed 5,500, with tens of thousands of additional candidates awaiting verification. At every stage of that growth, super-Earths and mini-Neptunes made up the largest slice of the catalogue. There is a catch, though, and it matters. Both transit surveys and radial velocity measurements are far more sensitive to planets that are close to their stars. A close-in planet transits more frequently, making it easier to confirm. It also exerts a stronger gravitational pull on its star, making the radial velocity signal larger. Planets in wider orbits, the kind of orbits the terrestrial planets of our solar system occupy, are harder to detect by either method. Earth itself, orbiting at 1 astronomical unit, would require at least 3 years of observation just to see 3 transits, and the radial velocity signal it produces is almost too small to measure with current technology. This means the catalogue is biased. It is full of close-in planets, because those are the ones we can find. The population of super-Earths on wider, longer period orbits is almost entirely invisible to us. What we have catalogued is likely a fraction of what actually exists. The bias in our detection methods, if anything, makes the absence of super-Earths in our own system harder to explain, not easier, because the census we have almost certainly undercounts them. One of the stranger features of the exoplanet census is a gap, a size range where planets almost never appear. When astronomers first started sorting exoplanets by size, they expected something smooth, a gradual distribution of worlds ranging from tiny rocky planets up through larger and larger bodies, with every size roughly as common as the next. That is not what they found. What they found instead was a distribution with 2 distinct humps and a valley between them. A valley that, by every reasonable expectation, should not be there. Here is the picture. Plot the sizes of the thousands of exoplanets found by Kepler against how often each size appears, and 2 peaks emerge. The first sits at roughly 1.4 Earth radii, compact, dense, rocky worlds a bit bigger than Earth but not by much. The second sits at roughly 2.4 Earth radii, larger, lighter, worlds wrapped in thick gaseous envelopes, sometimes called mini-Neptunes. Between them, centered around 1.8 Earth radii, is the gap. Planets in that size range exist, but they are strikingly rare. You find far fewer of them than you would expect if planet sizes were simply distributed at random across the range. The gap is clean enough and consistent enough that astronomers gave it a name, the Radius Valley. What makes this scientifically important is what it implies. If planets could form at any size and just sit there, you would expect a smooth count. The fact that planets cluster into two groups and avoid the space between them is telling you that something is actively sorting them. Either planets form across the full range and then something later pushes them into one group or the other, or the formation process itself has strong preferences and rarely delivers a world that falls in the middle. Either way, you are looking at a physical process with an opinion, a universe that has decided small planets should be one thing or another, with very little tolerance for the in-between. The leading explanation involves something called photoevaporation, and it is worth pausing on because it is genuinely strange. When a planet forms close to its star, it often holds on to a thin atmosphere of hydrogen and helium left over from the disk that built it in the first few 100 million years of a solar system's life. The young star is radiating intensely in X-rays and ultraviolet light. That radiation slams into the upper atmosphere of any nearby planet and heats it. If the planet is small enough and close enough, the gas at the top of the atmosphere moves fast enough to escape gravity entirely. It bleeds off into space. The planet loses its envelope. What remains is just the rocky core underneath. That core is now a smaller, denser world, the kind that shows up in the peak at 1.4 Earth radii. Larger planets, or planets that form slightly farther from the star and received less radiation, hold onto their hydrogen and helium. They stay puffy. They become the mini Neptunes sitting at 2.4 Earth radii. The gap is not a place where planets never existed. It may be a place where planets used to exist but couldn't stay. This model, called photoevaporation-driven atmospheric loss, has held up well against the data. The position of the radius valley shifts with orbital period in exactly the way you would predict if radiation stripping were the cause. Planets closer to their stars lose their atmospheres more easily, so the gap appears at smaller sizes for tighter orbits and larger sizes for wider orbits. When researchers mapped the valley across different orbital distances and compared those maps to the photoevaporation models, the match was striking. But there is a competing idea, and it is not going away. Some researchers argue the sculpting happens not from outside the planet, but from inside it. The mechanism here is called core-powered mass loss. The rocky core of a young planet retains heat from its formation for billions of years. That internal heat can drive its own slow atmospheric escape, independent of what the star is doing. The predictions from core-powered mass loss produce a radius valley in roughly the right place. Distinguishing the two mechanisms observationally is difficult because they make similar predictions about where the valley falls. The current evidence suggests that both processes probably operate, with photoevaporation dominating for younger planets on tight orbits and core-powered loss playing a longer, slower role. A third interpretation takes a different angle entirely. Perhaps the valley is not primarily the result of atmospheric loss at all. Perhaps it reflects something about how planets form in the first place. There is a growing body of work suggesting that the protoplanetary disk itself tends to produce either dense rocky planets or larger volatile rich worlds, with relatively few outcomes in between. In this picture, the formation pathways diverge early. The gap appears because the physics of accretion naturally steers embryos toward one end of the size range or the other. The sculpting still happens, just during formation rather than after it. What is clear is that the radius valley is not an accident of detection. Early on, some astronomers worried it might be an artifact of how Kepler measured planet sizes, a systematic bias in the data that made certain sizes look rarer than they really were. That concern has been largely put to rest. Improved stellar characterization, better radius measurements. Independent confirmation from other surveys have all confirmed the gap is real. It is in the data the way a fingerprint is in wax. Something put it there, and it is not going away when you look more carefully. The radius valley matters beyond its own puzzle because it sharpens the question of what super-Earths actually are. If many of them are stripped mini-Neptunes, former gas-shrouded worlds that lost their envelopes, then what we are cataloguing as rocky planets may have had very different early histories than their current forms suggest. They may be survivors of a more violent process. That complicates any simple comparison between super-Earths and Earth. It complicates any estimate of how many of them might be genuinely rocky worlds rather than bare cores of something that was once much larger. Whatever is happening, the radius valley is telling us that the universe has strong opinions about what size a small planet should be. The two answers it keeps giving are not the same answer our solar system gave. Planets do not spring into existence fully formed. Every planet in every system we have ever studied, including our own, started as something far smaller, a cloud of gas and dust orbiting a young star, slowly, violently, over millions of years, pulling itself together. Understanding how that process works is the only way to understand why it produces such radically different results in different systems. The same basic physics, operating on slightly different starting conditions, can end up building a solar system like ours or packing 6 super-Earths inside the orbit of Mercury. The physics is not mysterious. The starting conditions are everything. The dominant model for how rocky planets form is called core accretion. It begins in the protoplanetary disk, the flat spinning cloud of gas and dust surrounding a newborn star. Within that disk, microscopic grains of rock and ice collide and stick together. Over time, clumps form. The clumps grow into pebbles, pebbles into boulders, boulders into objects hundreds of kilometers across called planetesimals. Those planetesimals collide, sometimes shattering, sometimes merging, and slowly the survivors accumulate mass. A body that reaches roughly the size of Mars, about 1/10 of Earth's mass, becomes large enough that its own gravity starts doing most of the work. It begins pulling in nearby material more efficiently. The process accelerates. This is how you build a planetary embryo. This is how, over tens of millions of years, you end up with rocky worlds like Earth and Venus and Mars. The problem is the timescale. Core accretion through planetesimal collisions is slow, tens of millions of years slow, and the protoplanetary disk, the supply of material the embryos are drawing from, does not last forever. Most disks dissipate within about 10 million years as radiation and stellar winds from the young star blow the gas away. If you are relying only on planetesimal collisions to build your planets, you're racing against a clock. For Earth-sized worlds, the numbers work out, barely. For something much larger, built in the inner disk where material is sparse and distances between bodies are small, the numbers get uncomfortable. This is where Pebble accretion changes everything. In the last 20 years, researchers figured out that there is a much faster way to build a planetary core. Centimeter-scale particles, genuine pebbles roughly the size of a marble or a golf ball, behave very differently in a protoplanetary disk than larger chunks of rock. They spiral inward through the disk because of a drag effect, the gas disk rotating at a slightly different speed than the solid particles. That causes the pebbles to lose angular momentum and drift toward the star. A planetary embryo sitting in the path of that inward pebble drift is like a net stretched across a river. It catches material far more efficiently than it could by waiting for the occasional collision with another large body. A core growing by Pebble accretion can reach 10 Earth masses in a fraction of the time it would take through planetesimal collisions alone. This is fast enough to beat the disk lifetime. This is how you build a super-Earth. Here is the part that matters most. Which of these pathways a forming planet follows depends heavily on one thing: how large the Pebble flux is. The Pebble flux is the rate at which centimeter-scale particles are drifting inward through the disk. It depends on how much solid material the disk started with. A disk with a large Pebble flux produces embryos that grow fast, grow large, grow in the inner regions of the disk where the material concentrates most. A disk with a weaker Pebble flux produces embryos that grow more slowly, reach lower final masses, end up on wider orbits farther from the star. One pathway produces a solar system like ours, small rocky worlds spaced out across the inner system, none of them dramatically more massive than Earth. The other pathway produces something like what we see around most other stars, massive super-Earths stacked up in tight, close-in orbits, sometimes multiple worlds crammed inside a distance smaller than Mercury's orbit around our Sun. What separates these two outcomes is not some fundamental difference in the physics. Studies of disk formation have found that a difference in pebble mass flux of roughly a factor of 2 is enough to flip a system from one mode to the other entirely. Double the solid material available in the disk and you don't just get slightly bigger planets, you get a completely different class of planetary system. The same star, the same elements, the same gravitational physics. A factor of 2 in the initial supply of solid material produces a result so different that we would classify the two systems as belonging to almost separate categories. This is a strange and uncomfortable conclusion. It suggests that the specific architecture of our solar system was not inevitable. It was not the default output of planetary physics operating normally. It was one outcome, contingent on starting conditions that apparently most disks around other stars did not share. Most disks were richer in solid material, or configured in ways that sent more of that material flowing inward, where growing embryos could catch it and grow enormous before the gas dispersed. Our disk apparently was leaner. The Pebble flux feeding our inner solar system was not high enough, or did not last long enough, to push any of the early embryos past the threshold where they would have exploded in size and become the close-in super-Earths that crowd the inner regions of so many other systems. Whether that leanness was a property of the original cloud that collapsed to form our solar system, or whether it was produced by some event that interrupted the Pebble flow early, a giant planet forming and blocking the drift, a pressure structure in the disk, is a question the next few sections will have to answer. The line between a solar system that looks like ours and one packed with super-Earths on close orbits may come down to how much raw material the early disk had to work with, and what happened to that material in the first few million years. Most of the super-Earths we have found are not where they formed. That sounds like a small detail. It is not. It changes everything about how we understand planetary systems, and it is one of the central reasons the exoplanet census looks so different from our own solar system's architecture. To understand what happened to these planets, you need to understand something about the environment they formed in. For the first few million years of any planetary system's life, the young star is surrounded by a protoplanetary disk, a rotating structure of gas and dust stretching outward for billions of kilometers. This is the raw material of planet formation, and it is not a quiet place. Material flows inward, pressures vary across the disk. Temperature gradients shape everything, and anything embedded in that disk is subject to gravitational forces that push and pull in ways that are not always intuitive. When a planet grows large enough to have significant mass, but not large enough to carve a clean gap in the gas around it, something specific starts to happen. The planet interacts gravitationally with the disk material on both sides of its orbit. The gas slightly ahead of the planet pulls it forward. The gas slightly behind it drags it back. These two forces don't cancel out cleanly. The net result is a slow, steady loss of orbital energy. The planet spirals inward, not quickly by human standards, but on astronomical timescales, relentlessly. This is called Type 1 migration, and it operates on every planet below a certain mass threshold without requiring the planet to clear any gap at all. The disk itself is the engine. The rate depends on the planet's mass and the local density and temperature of the disk. More massive planets migrate faster. Denser disks drive faster migration. For a planet in the super-Earth range, say 5 Earth masses sitting a couple of AU from its star, the inward drift can be significant over hundreds of thousands of years. The planet that formed in the temperate middle region of the disk ends up much closer to the star than where it started. Now run this process forward in computer simulations, and the picture that keeps emerging is striking. Super-Earths don't just drift inward, they drift inward and pile up. As one planet migrates toward the inner edge of the disk, it may catch up to another planet that migrated ahead of it, or it may push into territory where the disk structure slows migration down. What you get is a chain of planets locked into what astronomers call mean motion resonances, orbital relationships where one planet completes a precise integer ratio of orbits for every orbit completed by its neighbor. 2 laps for every 3, 3 for every 4. The gravitational tugs between these planets keep them locked in step, the way a series of coupled pendulums will eventually synchronize. These resonant chains are a signature of migration. They don't form any other way, not cleanly, and not in multiples. When we find several super-Earths orbiting a star in tight resonant chains, we are almost certainly looking at planets that migrated there. This is why so many detected super-Earths orbit within a fraction of an AU of their host stars. Periods of 10 days, 5 days, 3 days. Surface temperatures high enough to melt rock on the day side. These planets are not in those positions because that's where they grew. The inner edge of a protoplanetary disk, near the magnetospheric cavity where the gas thins out and migration effectively halts, acts as a kind of parking zone. Planets drift in and stop there. Then more planets drift in behind them. The result is the tight, compact, resonant multi-planet systems that the Kepler survey found over and over again. What determines whether a planet completes that journey or stalls partway? The lifetime of the gas disk. This turns out to be a critical variable. Protoplanetary disks do not last forever. They are gradually dissipated by radiation from the young star, by stellar winds, and by a process called photoevaporation, where high-energy photons drive gas off the disk surface from the outside in. Most disks survive for somewhere between 1 and 10 million years after the star forms. That window is when Type 1 migration is possible. Once the gas is gone, migration stops entirely. A planet caught midway through its inward journey simply stays where it is when the gas disappears around it. This creates an enormous sensitivity to timing. A planet that forms early, when the disk is still thick with gas, has millions of years to migrate and will likely end up in a short period orbit. A planet that forms late, close to the moment the disk begins dispersing, may migrate only a short distance before the gas thins and its engine cuts out. The final orbital position of a super-Earth is not just determined by where it formed. It is determined by when it formed, how fast it grew, how long the disk lasted, and how many other planets were competing for the same migration pathway at the same time. It's a race with an unpredictable finish. What the simulations agree on, across a wide range of disk models and initial conditions, is that migration is not rare. It is the default. In a disk with enough solid material to build super-Earths, which most disks apparently have, those super-Earths will almost inevitably migrate toward their star unless something stops them. A giant planet already parked in the inner system can act as a barrier. A disk that evaporates unusually quickly can strand planets before they travel far. But absent those specific conditions, inward migration is what happens. The planets we find stacked up in close orbits around other stars are not exotic outcomes. They are what planetary systems normally produce when you leave the physics alone and let it run. Migration changed the architecture of virtually every planetary system we have observed, which makes it all the more striking that in our own system, nothing seems to have migrated into the inner region at all. Add up the mass of Mercury, Venus, Earth and Mars together, and you get a number smaller than a single typical super-Earth found around another star, not by a little. The combined mass of all 4 terrestrial planets in our solar system falls below 2 Earth masses. A mid-sized super-Earth, the kind that turns up routinely in Kepler data, can run 3, 4, 5 times that. Our entire inner solar system, every rocky world orbiting between the Sun and beyond Mars, would not qualify as one unremarkable planet in any of the systems we keep finding out there. This is what makes the problem so strange. It is not just that we lack super-Earths. It is that the inner region of our solar system is almost startlingly low mass by any standard the galaxy seems to recognize. The space between the Sun and roughly 1 astronomical unit, the distance Earth sits at, should be busy. Statistical surveys say most stars have something substantial there. Close-in planets, heavy ones, packed into tight orbits in the very region our solar system treats as nearly empty. Instead, we have Mercury, a world smaller than some moons. We have Mars, a planet so stunted that astronomers sometimes call it a failed planet. We have Venus and Earth, the 2 most massive of the 4, and even they fall far short of what other systems routinely produce in this same orbital range. Run the numbers from Kepler and the picture sharpens. Roughly 77% of Sun-like stars host planets in the super-Earth size range with orbital periods under 300 days. Many of those orbits sit well inside 1 AU. The inner disk around a typical star is not empty, it is full, often packed with multiple massive worlds stacked in tight resonant chains. Our solar system is the outlier. The vacancy in our inner region is not a minor deviation from the average. It is dramatic. It is the kind of absence that demands a specific explanation. Here is something worth holding on to. The question astronomers are really asking is not just why we have no super-Earths. Plenty of things can prevent a planet from forming. The deeper and harder question is why the inner solar system is so specifically, so completely depleted of mass in general. Whatever process shaped our planetary system did not merely fail to produce large planets close to the Sun. It left almost nothing there at all. That is a much stronger constraint. Any explanation for our missing super-Earths has to account for the low mass of what we do have, not just the absence of what we do not. The contrast with other systems is almost uncomfortable when you sit with it. Systems discovered by Kepler routinely show multiple planets interior to Earth's orbit, each one carrying several Earth masses. Some of those systems have more total mass inside 1 AU than our entire solar system has across all 8 planets combined. We are not a low-mass solar system that happened to skip the super-Earth size range. We are a low-mass inner solar system by a margin that seems almost deliberate. What could have produced this? Researchers have been working on this problem seriously for roughly 2 decades, and the honest answer is that no single mechanism cleanly accounts for everything. The most obvious possibility is that the raw material to build large planets was simply never there in the inner disk to begin with. If the protoplanetary disk that formed our solar system was naturally depleted of solid material close to the Sun, then the terrestrial planets we ended up with may represent more or less the maximum the disk could build. No catastrophe needed, just a lean starting inventory. But that explanation runs into trouble quickly. Other young planetary systems observed today show clear evidence of solid-rich inner disks, full of the dust and pebbles that planet formation feeds on. If our disk was unusually lean, that itself needs explaining. It was not the default. A second possibility is that the material was there, but something blocked it from reaching the inner disk. Giant planets forming in the outer solar system can act as barriers, stopping the inward flow of pebbles that rocky embryos need to grow. If something massive formed early enough and far enough out, it could have starved the inner disk of building material before any large planets had a chance to assemble. The inner solar system would end up depleted, not because it started lean, but because its supply was cut off. A third possibility is the most dramatic. Maybe the inner solar system built large planets and then lost them. Planetary embryos growing in the inner disk, disrupted by the gravitational influence of a migrating giant planet, driven into the Sun. What we see today, Mercury, Venus, Earth, Mars, could be a second generation assembled from the wreckage, inheriting far less mass than the first round of planet formation had accumulated. The inner solar system would be depleted because most of its mass was already gone before our current planets even began to take shape. Each of these explanations has evidence behind it. Each of them also has gaps. The disk depletion model struggles to explain why our inner disk would be so specifically lean when most other stars do not appear to share this condition. The Pebble barrier model requires a giant planet forming quickly enough and in the right place to cut off the supply before the inner disk fills up. The destruction model requires a migration history violent enough to sweep the inner system nearly clean while still leaving enough debris to form 4 planets afterward. None of them is obviously wrong. None of them alone is obviously complete. 3 separate explanations have been developed to account for why our inner solar system is so empty, and the unsatisfying truth is that all 3 may be partly right. One explanation starts before a single planet existed, before even the first pebbles had stuck together. It begins with the solar nebula itself, the vast, swirling disk of gas and dust that surrounded the young sun roughly 4.6 billion years ago. The question is not what happened to the super-Earths that tried to form. The question is whether the raw material to build them ever made it to the inner disk in the first place. To understand why this matters, you have to understand how planets actually get their building material. In the early disk, tiny solid grains, dust, ice, silicates, stick together and grow into centimetre-scale pebbles. Those pebbles spiral inward through the disk toward the star, carried along by the gas. As they drift, they become the supply chain for growing planetary embryos. Wherever pebbles concentrate, planets have material to work with. Wherever the supply is cut off, planets starve. The inner solar system, according to this hypothesis, was the region that starved. The mechanism responsible is something called a pressure bump. In a smooth, uniform disk, pebbles drift inward steadily. But the disk is not smooth. At specific distances from the young sun, something changes. Certain ices, water, carbon monoxide, other volatile compounds, reach the temperature at which they vaporize. These transition zones, called sublimation fronts or snow lines, release sudden bursts of gas as solids turn to vapor. That release creates a local region where the gas pressure is slightly higher than the surrounding disk. Pebbles drifting inward hit this pressure gradient and stop. They pile up at the bump like debris caught against a dam. They do not cross it. They sit there and accumulate, building a ring of solid material, while the inner disk receives nothing. The solar system would have had several of these sublimation fronts, each corresponding to a different volatile. The water snow line, the point where water ice transitions to vapor, sits at roughly the distance of the asteroid belt today. There would have been similar fronts at different distances for carbon monoxide ice, for carbon dioxide, for other compounds. Each one was a potential barrier. Each one was a place where inward drifting pebbles could have been trapped and held, never reaching the region where Earth and its neighbors eventually formed. If this picture is correct, then the inner solar system's mass deficit is not strange at all. It is expected. The disk did not fail to produce super-Earths because something disrupted the process midway through. It failed to produce them because the pebble supply was intercepted at the source before the process could begin. The inner region was not a construction zone that got destroyed. It was a construction zone that never received its materials. What makes this more than just a theoretical argument is what telescopes have found around other young stars. Over the last decade, high-resolution images from instruments like the Atacama Large Millimeter Array, ALMA, have revealed that protoplanetary disks around young stars are not smooth at all. They are structured. Almost every young disk that has been imaged in detail shows rings and gaps, bright annuli of concentrated dust separated by dark regions where solid material is sparse. These rings appear at distances that match, at least roughly, the locations where sublimation fronts or other pressure barriers would be expected to exist. This was not what anyone anticipated. Before ALMA, the working assumption was that protoplanetary disks were relatively uniform, with material distributed smoothly and pebbles free to drift wherever the physics took them. The images showed something fundamentally different. Structure is apparently the default, not the exception. Disks sort themselves into rings almost as a matter of course. The smooth disk was the textbook diagram. The ringed disk is what actually exists. For our solar system, this changes the framing of the question entirely. If rings are the normal outcome of disk physics, then the relevant issue is not whether our early disk had rings. It almost certainly did, but where those rings sat and how efficiently they blocked the inward pebble flux. A disk with pressure bumps positioned in just the right locations could have sequestered a large fraction of the available solid material into the outer ring structures, leaving the inner disk starved. The narrow, low-mass terrestrial planets we ended up with would then be the predictable result of a disk that hoarded its solids in the wrong places. Researchers modeling this scenario have found that the positions of pressure bumps depend on the disk's temperature profile, its composition, and its density structure, all of which vary from system to system. Most systems apparently allow enough pebbles through to build substantial inner planets. Our disk, for reasons that may come down to its specific initial mass and thermal structure, may have been more effective at trapping material early. The annuli that formed were not loose, leaky accumulations. They were efficient barriers that held onto their pebbles and starved the inner disk of the supply it needed to build anything large. There is something quietly striking about this explanation. It requires no catastrophe, no giant planet smashing through the inner system, no dramatic instability, no collision cascade, just a disk that was structured in a particular way, with pressure bumps sitting in positions that happened to intercept the pebble flow before the inner region could accumulate enough mass to produce super-Earths. The outcome was determined not by a violent event, but by geometry, by where certain temperature thresholds happen to fall in our particular disk, around our particular star, at this particular moment in galactic history. If the rings were real, and the evidence from other young systems suggests they probably were, then the solar system's inner region was starved of material almost from the beginning, long before anything large enough to call a planet had formed. Jupiter did not just form fast, it formed so fast that it changed everything happening in the rest of the solar system before the other planets had time to respond. To understand why that matters, you need a picture of what the early solar system looked like before any planet had fully assembled. There was the young sun at the center. Surrounding it, a vast rotating disk of gas and dust and trillions of tiny pebbles, maybe a centimeter across, drifting slowly inward. Those pebbles were the raw material. They collided, stuck together, and gradually built larger and larger objects. Most planetary formation models assume this process takes tens of millions of years. Jupiter did not wait that long. Current estimates put Jupiter's core formation at somewhere between 1 and 3 million years after the Sun ignited. That is extraordinarily fast by any standard in planetary science. For comparison, Earth took somewhere around 50 to 100 million years to reach its current mass. Jupiter did not just beat Earth to the finish line, it was essentially done before Earth had even started. The reason is that Jupiter formed in a colder region of the disk, beyond what planetary scientists call the snow line. The distance from the Sun where temperatures drop low enough for water to freeze into ice. Beyond the snow line, the solid material available to build a planet's core was dramatically more abundant. This was because ice counted as a solid, not just gas. Jupiter's birthplace gave it access to far more building material than the inner disk ever had. Here is where it gets important. Once Jupiter's core grew large enough, somewhere around 10 to 20 Earth masses, it became massive enough to do something no smaller object could do. It began to gravitationally dominate the region around it, and critically, it began to act as a barrier to the inward flow of pebbles drifting from the outer disk toward the Sun. Those drifting pebbles were not just background clutter, they were the supply chain feeding the entire inner solar system. Pebbles from the cold outer regions spiral inward through gas drag. As they move through the disk, they become available to growing planet embryos along the way. The inner disk depended on that steady inward flow of material to keep building mass. When Jupiter's growing core reached a critical size, it created a pressure bump in the gas disk just outside its orbit. That pressure bump stopped the pebble drift cold. Pebbles that would have continued inward piled up at the barrier instead. The supply to the inner disk was cut off. Think of it like a dam in a river. Everything upstream of Jupiter kept receiving material. The outer solar system had all the pebbles it needed to build Saturn, Uranus, Neptune. Whatever else formed out there, everything downstream, meaning everything between Jupiter and the Sun, suddenly found itself working with a fixed and dwindling supply. No new material was coming in. Whatever mass was already present in the inner disk was all the inner disk was ever going to get. The numbers here are striking. The inner solar system today, Mercury, Venus, Earth, Mars combined, contains roughly 2 Earth masses of solid material. A typical super-Earth found around another star weighs somewhere between 2 and 10 Earth masses all by itself. The inner solar system doesn't just lack super-Earths, it lacks the mass that would have been required to build them. And the Pebble barrier Jupiter created is one of the primary reasons why that mass never arrived. What makes this scenario so significant is the timing. If Jupiter had taken 20 or 30 million years to form instead of 1 to 3 million, the inner disk would have had decades more of Pebble delivery to work with. Planetary embryos in the inner system would have grown larger, accumulated more mass, potentially crossed the threshold needed to become super-Earths. They might then have migrated inward, stacked up near the Sun, produced exactly the kind of crowded, close-in system that Kepler found around hundreds of other stars. Jupiter's early arrival foreclosed that possibility before it could develop. There is a deeper strangeness here worth sitting with. Jupiter's rapid formation may itself be a consequence of the outer disk's unusual richness in solid material. Jupiter formed where it did because conditions beyond the snow line were especially favorable. But in forming so quickly and so massively, it reshaped the conditions everywhere else. One planet, growing fast in the right place at the right moment, quietly starved the rest of the system. The inner solar system never knew what it was missing. This was because the barrier was in place before anything large enough to benefit from more material had even assembled. This is not a minor footnote to the story of our solar system. It is potentially one of its central facts. Researchers modeling the Pebble accretion process have found that the difference between a disk that produces super-Earths and one that produces small rocky planets can hinge on whether a giant planet forms early enough to interrupt the Pebble flow. In simulations where no early giant forms, pebbles stream freely into the inner disk. Planetary embryos grow large. Super-Earths appear on tight orbits just as they do in observed exoplanet systems. In simulations where a giant planet forms fast enough and far enough out, the flow is blocked, the inner disk stays lean. The final planets are small. Our solar system in this picture followed the second path entirely because Jupiter happened to win the formation race. None of this means the picture is complete. The Pebble barrier explains a depleted inner disk, but it does not fully explain the specific architecture of what is there. Other forces were still at work, and we will get to them. But Jupiter's early formation stands as perhaps the single most consequential event in determining why our solar system looks the way it does. By the time the inner solar system had any hope of building super-Earths, the material to build them with had already been blocked by a planet 4 times larger than all the others combined. The Grand Tack is a theory that sounds almost too violent to be true. Jupiter, the largest planet in the solar system, once drove itself toward the Sun. Not a little, not a nudge. Jupiter, which sits today at 5 times Earth's distance from the Sun, appears to have migrated inward far enough that its closest approach brought it somewhere between 1.5 and 2 astronomical units, roughly where Mars orbits today, or just inside it. That is a planet more than 3 times the mass of everything else in the solar system combined. ploughing through the inner disk like a slow-moving catastrophe. The name comes from sailing. A tack is when a sailing ship swings its bow across the wind and reverses its direction. It came in, and then it came back out. The entire inner solar system was never the same. To understand how this happens, you need to know how large planets interact with the disk they form inside. When a planet reaches a certain mass, something close to Jupiter's mass, it carves a gap in the gas and dust around it. The planet clears out an annulus of material, and then it starts to drift. Gas on the outer edge of that gap exerts a gravitational pull, and gas on the inner edge exerts a slightly weaker one, and the net effect is that the planet migrates inward. This is called Type 2 migration, and it is not exotic or unusual. It is the standard expectation for any planet massive enough to open a gap in its disk. Most giant planets in other systems that we find on tight inner orbits almost certainly got there exactly this way. The strange thing is not that Jupiter started migrating. The strange thing is that it stopped. Jupiter began drifting inward, sweeping material in front of it and scattering material behind it. As it moved, it compressed the inner disk. Planetesimals and embryos that had been growing in the region between 1 and 3 astronomical units were being pushed, scattered, captured into resonances, or flung outward entirely. The feeding zone that should have been producing a generation of substantial planets was being systematically dismantled. Jupiter wasn't forming those planets. It was unforming them. Then Saturn caught up. Saturn formed later than Jupiter, and when it reached sufficient mass to open its own gap in the disk, it too began migrating inward. Crucially, Saturn migrated faster than Jupiter. Saturn closed the distance. When it finally caught up, something that sounds almost accidental, but is actually a well-understood gravitational outcome occurred. Saturn was captured into a 3-to-2 mean motion resonance with Jupiter. For every 3 orbits Jupiter completed, Saturn completed 2. They were locked together. That locking changed everything. A single giant planet migrating inward through a disk will keep migrating inward until the disk is gone, or until it falls into the star. 2 giant planets locked in resonance do something different. The combined gravitational geometry of the pair reverses the net torque from the surrounding disk. Instead of being pushed inward, they are pushed outward. The migration flipped. Jupiter and Saturn, now moving as a coupled system, began drifting back out toward the positions they occupy today. The inward journey ended. The tack was complete. Jupiter's turnaround point was somewhere around 1.5 to 2 astronomical units. That number matters. It means Jupiter came close enough to do severe damage to the inner solar system, but stopped short of destroying it completely. Had Jupiter reached 1 AU, the region where Earth now orbits would have been swept clean down to essentially nothing. At 1.5 to 2 AU, enough debris survived the encounter to eventually assemble into rocky planets. Not big ones. Not super-Earths, but something. What the inward passage did to the asteroid belt is dramatic and well documented in the geological and dynamical record. The asteroid belt today is famously empty. The total mass of all the asteroids combined is less than 4% of Earth's mass. For a region that size, sitting that close to the Sun with that much raw material once available, that is an extraordinary deficit. Models of solar system formation without the Grand Tack produce an asteroid belt far more massive than the one we observe. The Grand Tack scenario depletes it to roughly the right level by having Jupiter's passage scatter most of the material out of the region entirely. Some inward, some into the outer solar system, most just gone. Mars tells a similar story. Mars is small. Standard planet formation models that don't invoke something like the Grand Tack predict a Mars several times more massive than the one we have. The actual Mars is roughly 1/10 the mass of Earth. Its feeding zone, the region from which it could have gathered material through gravity, was depleted before it had time to grow. Jupiter's inward passage swept through that region. The material that should have built a larger Mars was scattered away before Mars could collect it. What we ended up with is essentially a stunted embryo, a planet that never got to finish forming because the material it needed was removed from the neighborhood. The planetary embryos that had already grown in the region between roughly 0.5 and 2 astronomical units fared even worse. Some of those embryos, had Jupiter never migrated, might have continued accumulating material and eventually reached super-Earth masses. Instead, Jupiter's passage disrupted their orbits. Objects that had been on nearly circular, stable orbits were thrown onto eccentric ones. Eccentric orbits mean more energetic collisions, more scattering, more objects being flung inward or outward. The orderly process of accretion that builds planets was replaced by the chaotic process of dispersal that destroys them. Whatever was growing in Jupiter's path either fell into the Sun, was ejected outward, or was ground back down into smaller fragments over subsequent millions of years. The outward migration, the second half of the tack, didn't undo the damage. By the time Jupiter and Saturn reversed course and drifted back out to their current positions, the inner disk had already been devastated. The material was gone. The embryos that had survived were smaller, fewer, and scattered across wider orbits. The outward migration pushed some of the outer asteroid belt's material inward, which is why the asteroid belt today contains two chemically distinct populations: rocky inner belt objects and more volatile, rich outer belt objects that were reshuffled during Jupiter and Saturn's retreat. But none of that reshuffling put back the mass that had been lost from the inner solar system. There is something almost hard to sit with about this picture. Our solar system came within a factor of 2 or 3 of looking like every other system in the galaxy. Had Jupiter's turnaround point been at 2.5 AU instead of 1.5, the damage to the inner solar system would have been less severe. Had Saturn not caught up quickly enough to lock Jupiter in resonance, Jupiter might have kept migrating all the way in, stranding itself in a close orbit and leaving the inner system in ruins. Had Saturn formed earlier and caught up before Jupiter had travelled so far, Jupiter would have reversed course sooner and done less damage. The margin between what we have and what we could have had is thin. The Grand Tack left the inner solar system battered and depleted, with just enough material scattered about to eventually form the 4 small rocky worlds we live among today, and not enough to have built anything bigger. There is a version of our solar system's early history in which super-Earths existed, and then they didn't. The Grand Tack gives us Jupiter charging inward, and then retreating, leaving the inner solar system battered. But there is a hypothesis that goes further than that. One that asks a question most planetary scientists did not seriously consider until the exoplanet data made it unavoidable. What if the inner solar system did not simply fail to build super-Earths? What if it built them, lost them, and then built something smaller from what was left? What if Mercury, Venus, Earth and Mars are not the first generation of inner planets, but the second? This idea has a name in the literature. Some researchers call it the sequential formation model. Others refer to it more bluntly as the obliteration scenario. The version developed by researchers including Mac Clement at the Carnegie Institution frames it this way. Before Jupiter's migration swept through the inner disk, planetary embryos were already accumulating mass in the region now occupied by our rocky planets. These were not small objects. Given the timescales involved and the density of material in early protoplanetary disks, some of those embryos likely reached masses comparable to what we now classify as super-Earths. Several Earth masses, maybe more, growing fast in tight orbits, doing exactly what planetary embryos do when the conditions are right. Then Jupiter arrived. When Jupiter began its inward migration through the disk, the gravitational consequences for the inner system were severe. A planet that massive moving through that region does not simply pass by. It perturbs everything near its path. Orbital resonances sweep through the inner disk like a wave, pushing embryos onto increasingly eccentric trajectories. Objects that had been growing steadily in stable orbits found themselves on paths that crossed other orbits, crashed into neighbors, or gradually spiraled inward under the combined gravitational pressure of the disk and Jupiter's influence. The inward spiral is the key part. A planet losing angular momentum to disk interactions has only one direction to go. It falls toward the Sun. It does not survive the encounter. The model proposes that one by one, the first-generation embryos destabilized, fell inward, and were consumed. The Sun grew slightly heavier with each one. The inner solar system was left emptied, not because it lacked material to begin with, but because what it built was taken away before it could survive. When Jupiter eventually reversed course and migrated back outward, pulled by Saturn locking into resonance, the destruction was already done. What remained was a scattered, low-density field of smaller rocks and fragments, the debris of a planetary generation. From that debris, a second generation of planets formed, smaller ones, the embryos that became Mercury, Venus, Earth, and Mars grew from what was left after the cleanup. This explains something that has puzzled researchers for a long time. The total mass of all 4 terrestrial planets is strikingly low compared to what disk models predict should have been available in that region. You would expect more mass. You would expect bigger planets. The models that try to form our rocky planets directly from the original disk have always struggled with this discrepancy. The sequential formation model resolves it by saying the first round of assembly was erased, and what we are modeling as the starting material for the terrestrial planets themselves. Mars is much smaller than you would expect if it formed freely in a material-rich environment. It is roughly 1/10 the mass of Earth, even though it sits at a position in the disk where accretion should have gone reasonably well. One long-standing explanation is that Jupiter's early influence starved Mars's feeding zone, preventing it from accumulating much mass. But the sequential formation model offers a different angle. Mars may simply be a remnant object, something that formed after most of the available material had already been processed, disrupted, and lost. A planet that never got the chance to grow properly because the conditions that would have allowed it were swept away. Mercury fits the picture too, in a different way. Mercury is dense, denser than any other planet in the solar system relative to its size, with an iron core that takes up a disproportionately large fraction of its interior. Several mechanisms have been proposed to explain this, including a giant impact that stripped away its rocky mantle. But some versions of the sequential formation model suggest that Mercury's unusual composition could reflect its origins in the most chaotic period of inner disk evolution, when violent collisions and gravitational stripping were common, and objects were being pushed to extremes before the system settled. What makes this hypothesis striking is not just the mechanism but the implication. It means that our solar system is not simply a case where super-Earths failed to form. It is potentially a case where super-Earths formed, thrived briefly, and were destroyed so thoroughly that they left almost no direct record. The sun absorbed the evidence. The only signs that something large once occupied the inner disk are the strange mass distribution of the planets that replaced them and the mathematical difficulty of explaining those planets without invoking some prior clearing event. The ghost of a first generation, visible only in the shape of what came after. This is a harder hypothesis to test than the disk depletion model or the Pebble barrier concept. Planets that fell into the Sun 4 billion years ago left no recoverable fossil. We cannot point to a missing planet. We can only point to the low-mass system we have, run the models forward and backward, and notice that the numbers work out better when you include a first generation that no longer exists. That is a different kind of evidence. It is the absence of something where the math says something should have been. The terrestrial planets we live among might be the second attempt, built from whatever was left after the first generation fell into the Sun billions of years ago, leaving almost no trace. Each of the three major explanations for our solar system's missing super-Earths is compelling on its own and insufficient on its own. That is not a comfortable place to land. Scientists generally prefer clean answers. One cause, one effect, one mechanism that accounts for the data. With super-Earths, that clean answer has not arrived. What has arrived instead is something more complicated and, depending on your tolerance for ambiguity, more interesting. Start with the disk depletion model. The argument is straightforward. The protoplanetary disk that surrounded our young sun simply did not have enough solid material in the inner region to build large planets. Pressure bumps at certain distances trapped pebbles in rings before they could spiral inward. The inner disk was starved early. This explanation has real observational support behind it. Other young stellar systems observed with modern radio telescopes do show ring structures in their disks. The physics is understood. The problem is that disk depletion alone cannot fully explain how thoroughly the inner solar system ended up depleted. You can get a low-mass inner system from a modest reduction in pebble supply, getting almost nothing. Mercury at a fraction of an Earth mass, Mars at barely a tenth, requires something more extreme than rings and pressure bumps acting alone. The model reduces the problem. It does not solve it. Move to the Pebble barrier that Jupiter created. Jupiter formed fast, probably within the first few million years of the solar system's existence, and once it grew large enough to open a gap in the disk, pebbles from the outer solar system could no longer spiral past it. The inner disk was cut off from its supply line. This is a genuine and probably significant effect. Simulations show that a barrier at Jupiter's position would have substantially reduced the mass budget available for building close-in planets. But here is what the Pebble barrier cannot account for. There was already solid material inside Jupiter's orbit when Jupiter formed. That material did not vanish because the outer supply was cut off. Something had to remove or scatter what was already there, and a Pebble barrier sitting at 5 astronomical units does not reach back into the inner solar system to do that job. The barrier explains why the inner system could not grow further. It does not explain why what had already accumulated went away. That gap is where the Grand Tack scenario steps in. Jupiter's inward migration and its reversal once Saturn caught up and the two planets locked into resonance, drove through the inner solar system like a plough. Any large embryos growing in tight orbits would have been scattered, destabilized, pushed onto trajectories that eventually sent them into the sun. The Grand Tack can account for the kind of mass removal that disk depletion and the Pebble barrier cannot. It provides an active clearing mechanism rather than just a passive starvation of supply. The difficulty is that the Grand Tack requires a very particular sequence of events to work. Jupiter has to migrate inward to a specific distance, roughly 1.5 to 2 astronomical units, not further. Saturn has to catch up at precisely the right time. The resonance has to hold. The two planets have to reverse course and migrate outward before the disk fully dissipates. Any number of things along that chain could have gone differently, and if they had, you would get a completely different solar system architecture. The scenario is physically plausible. It is also, by the standards of planetary systems we have observed elsewhere, quite specific in what it demands. Each of these three mechanisms has a domain where it does real explanatory work, and a domain where it falls short. Disk depletion sets up the initial conditions, but cannot do the heavy lifting alone. The Pebble barrier prevents replenishment, but does not clear what is already there. The Grand Tack clears the inner system but requires a migration history that is far from guaranteed. The absence in our solar system is not modest. It is dramatic. Getting from a typical protoplanetary disk to our particular outcome probably required all three of these things, or something close to all three, operating more or less simultaneously. Think about what that means statistically. In a typical system, the disk is rich enough in pebbles to feed super-Earth formation in the inner region. In a typical system, whatever giant planets form do not execute a perfectly timed inward and then outward migration through that same region. In a typical system, Pebble barriers either do not form or form too late or too far out to matter. Our solar system appears to have run a sequence that combined an unusual disk structure, an unusually rapid giant planet formation, and a migration history that hit a very specific target. Each of those conditions alone might be uncommon. All three together, in the same system, at the right time, starts to look like a rare outcome. This does not mean no other star has a solar system like ours. The galaxy contains hundreds of billions of stars and enormous spans of time. Rare things happen constantly, but it does mean that the systems packed with close-in super-Earths, which dominate the exoplanet census at every stage of the data, are probably not the outliers. We are the outliers. The question is not why other systems built super-Earths. The question is why we went through a sequence of events unusual enough to end up without them. The honest conclusion is that our solar system's unusual architecture was probably not the result of a single decisive event. It was the product of several improbable things going right or wrong, depending on how you look at it, at the same time. Many of the super-Earth's astronomers have catalogued are not what they started out as. They look like rocky planets now. They probably began as something considerably larger, and the process that transformed them is one of the more violent things a young star routinely does to its neighbours. When planetary systems are young, the host star is not the calm, steady object it becomes in middle age. Young stars burn hot in X-ray and ultraviolet wavelengths. The output in those high-energy bands can be hundreds of times stronger than anything our current sun produces. For planets orbiting close in, that radiation does not just warm the surface, it tears into the atmosphere. High-energy photons collide with gas molecules in the upper layers, transferring enough energy to push them above escape velocity. The atmosphere does not leak slowly, it boils away. Astronomers call this photoevaporation, and in the right conditions it can strip a planet's entire gaseous envelope in a few 100 million years. That is fast by planetary timescales, fast enough to happen before the system has even settled into its mature configuration. Here is what makes this consequential. Most planets that form in the inner regions of a protoplanetary disk do not start out as bare rock. They accumulate a primordial atmosphere of hydrogen and helium left over from the disk itself. These envelopes can be thin or thick depending on how much gas the planet captured before the disk dissipated. A planet with a small rocky core and a modest hydrogen envelope might measure around 2.5 Earth radii. Strip that envelope away entirely, and the same planet measures closer to 1.4 Earth radii. Same mass underneath, completely different observable size. The radius valley sits exactly between those two outcomes. The valley itself runs from about 1.5 to 1.8 Earth radii. Almost no confirmed exoplanets fall in that range. Below it, you have a cluster of smaller, likely rocky worlds. Above it, a cluster of larger worlds that held on to their gas. The gap is not subtle. When you plot planet sizes against orbital period, the valley is one of the cleanest features in the entire exoplanet catalogue. Something is selecting strongly for one outcome or the other and leaving very little in between. Photoevaporation explains this naturally. A planet's fate depends on two things: how massive its rocky core is and how much radiation it receives. A smaller core at a tight orbit has weak gravity and strong irradiation, a bad combination for atmosphere retention. Its envelope gets stripped in short order. A larger core farther out has stronger gravity and less radiation. It keeps its gas and stays in the mini-Neptune regime. The boundary between those fates, predicted by the physics of atmospheric escape, falls right where the observed valley sits. This is not approximate. Researchers ran the models before the valley was confirmed statistically, and the location they predicted matched what Kepler then found in the data. That kind of agreement between theory and observation is rare enough that astronomers pay attention when it happens. There is a second mechanism that can produce a similar outcome. Core-powered mass loss works on a longer timescale than photoevaporation. In this scenario, the heat stored inside the planet itself, left over from the violence of formation, slowly diffuses outward and drives atmospheric escape from below rather than above. The radiation from the star matters less. The internal heat of the rocky core matters more. Both mechanisms produce a similar radius valley in models. The debate over which one dominates is still active, and the honest answer is probably that both operate in different contexts and for different classes of planets. What this means for the super-Earth census is something worth sitting with. When astronomers count super-Earths in the exoplanet catalogue, a significant fraction of those worlds were probably not born as super-Earths. They started larger. Some were mini-Neptunes or something close to it. Their atmospheres existed and then were destroyed. The rocky objects we detect today are the residue of that destruction. The original population of close-in planets may have looked considerably more uniform before stellar radiation sorted them into two distinct groups. You are not seeing the planets as they formed. You are seeing what the star did to them over the first few billion years. This matters because it changes how you interpret the numbers. If many super-Earths are stripped cores, then the apparent abundance of rocky planets in close orbits reflects not just how many rocky planets form, but how efficient stellar radiation is at removing atmospheres. Systems around more active stars might produce more stripped super-Earths, even if the initial planet population was identical to quieter systems. The observed distribution is the result of formation and then a long process of atmospheric sculpting acting on top of it. Separating those two contributions is one of the harder problems in the field right now. There is also the question of what survives the stripping process intact. Not every close-in planet loses everything. Some retain a thin secondary atmosphere built from volcanic outgassing after the primordial envelope is gone. Some may hold on to enough that the distinction between a stripped super-Earth and a low-mass mini-Neptune becomes ambiguous. The radius valley is a statistical feature, not an absolute wall. Individual planets blur the boundary in ways the simple models do not fully capture. Measuring actual atmospheric compositions for planets on either side of the valley is something that facilities like the James Webb Space Telescope are now beginning to do, and the results are already complicating the clean picture that photoevaporation models produce. What we classify as a super-Earth may often be a ghost of a larger planet, a world that once had an atmosphere and lost it, stripped down to its core by the radiation of a young and violent star. 40 light-years away, in the direction of the constellation Aquarius, a small dim star is doing something our Sun never did. It built 7 rocky worlds, packed them into a space smaller than Mercury's orbit, and placed 3 of them in a zone where liquid water could theoretically sit on an open surface. 7 planets. 1 star. All of them roughly Earth-sized. None of them anything like what our solar system produced. The star is called TRAPPIST-1. It is an ultra-cool red dwarf, barely larger than Jupiter, burning so faintly that it would be invisible to the naked eye, even from a neighboring star system. It is not a dramatic object. It was not famous before 2016. A Belgian-led team using a small ground-based telescope called TRAPPIST, the Transiting Planets and Planetesimals Small Telescope based in Chile, caught the first hints of multiple planets crossing the star's face in transit. The signal was faint, the star was dim, and the planets were close enough together that their transits overlapped in strange patterns. Follow-up observations with the Spitzer Space Telescope and Hubble confirmed the picture. By 2017, the full system had been announced. 7 planets, all detected through the transit method, all of them producing the tiny, repeating dips in starlight that tell astronomers something is passing between them and the star. The scientific community reacted with something close to disbelief. Not because the finding was implausible, but because the system was almost absurdly full. Every one of those 7 planets orbits closer to TRAPPIST-1 than Mercury orbits our Sun. The innermost planet completes a full year in about 1.5 Earth days. The outermost takes just under 20 days. By any standard derived from our solar system, these are scorchingly tight orbits. But TRAPPIST-1 is so cool and so dim that even at those distances, 3 of the planets, designated E, F, and G, receive roughly the same amount of energy that Earth receives from the Sun. They sit in what astronomers call the habitable zone, not guaranteed to be habitable, but in the right energy range for surface liquid water if other conditions cooperate. The physical properties of these planets have been measured in remarkable detail, given how far away they are. Their sizes come from transit photometry, how much starlight they block. Their masses come from transit timing variations, a technique that uses the subtle gravitational tugs the planets exert on each other to calculate how heavy they are. Every time one planet passes in front of the star, the others pull on it slightly, making the transit arrive a little earlier or later than a perfectly isolated orbit would predict. Those timing offsets, accumulated over hundreds of transits, let researchers work backward to the masses. The results produce something unexpected. When the masses and radii are combined to calculate density, the TRAPPIST-1 planets come out roughly 8% less dense than Earth. All 7 of them, consistently. That 8% difference is not noise. It is a signal about composition. Earth is dense partly because of its iron core. About a third of Earth's mass sits in a metallic center. The TRAPPIST-1 planets, to be uniformly less dense than Earth, must have either smaller iron cores or more low-density material mixed into their bulk, or both. Some models suggest they contain proportionally more water or other volatile compounds locked into their rocky structure than Earth does. Others suggest a lower iron fraction throughout. What it means is that these worlds, while Earth-sized in radius, are built from a different recipe. They are rocky, almost certainly, but the rock is not identical to ours. Planet E is the one that gets the most attention in habitability discussions. Its mass is about 77% of Earth's, its radius about 91%, and the energy it receives from TRAPPIST-1 falls close to what Earth receives from the Sun. If it has an atmosphere of any kind, surface temperatures could plausibly support liquid water. Planets F and G are colder, farther out, receiving less energy, and could have frozen surfaces or thin, cold atmospheres. Planet B, the innermost, is almost certainly too hot. Planet D sits at the inner edge of the habitable zone and receives somewhat more energy than Earth. Planet H, the outermost, orbits in permanent cold. None of them have confirmed atmospheres. Hubble searched for the thick hydrogen envelopes that would signal a more Neptune-like composition and found nothing, which is mildly encouraging. It suggests the planets are not gas-dominated, but detecting a thin nitrogen-oxygen atmosphere like Earth's from 40 light-years away is beyond current instruments. The James Webb Space Telescope has begun studying TRAPPIST-1 planets in infrared, looking for temperature signatures and atmospheric absorption features. Early results from Planet B suggested little to no atmosphere, which is not promising for that particular world. The others remain open questions. What makes TRAPPIST-1 significant beyond the headlines is what it illustrates about planetary formation around red dwarfs. M-dwarfs like TRAPPIST-1 are the most common stars in the galaxy by a large margin. They account for roughly 70% of all stars, and their occurrence rates for rocky planets are extraordinarily high. Some estimates place it above one super-Earth-sized planet per M-dwarf star on average. TRAPPIST-1 did not build one such planet, it built 7. The system is almost a demonstration case for what happens when a protoplanetary disk around a cool, low-mass star runs the formation process to completion. The planets are small, tightly packed, likely built through inward migration and resonance capture, which is why they all sit in chains of near-integer orbital period ratios, a signature of planets that drifted into their current positions rather than forming there. Our solar system has nothing like this. 8 planets, 4 of them rocky, none of them in the inner region where TRAPPIST-1 keeps all 7 of its worlds. The closest analogue we have to a packed inner system is empty space, stretching from Venus inward to the Sun with nothing but Mercury, which is itself a small battered remnant of something that may have once been larger. TRAPPIST-1 is what happens when a planetary system works the way the statistics say most planetary systems should work, and the result is a lineup of worlds that would have been called science fiction before the first exoplanet surveys came in. The closest planet outside our solar system is a super-Earth, and it is 4.2 light-years away, orbiting the faint red star just visible to the naked eye in the southern constellation Centaurus. That star is Proxima Centauri, the closest stellar neighbour our Sun has, and in 2016 a team of astronomers announced something remarkable about it. It had a planet. The discovery came through radial velocity measurements, the same technique that detects the subtle wobble a planet induces in its star as it orbits. The signal was clean. The period was 11.2 days. The minimum mass came out to just over 1 Earth mass, placing it firmly in the super-Earth category. For a moment, the world paid attention. The nearest star to our Sun, it turned out, was not alone. The orbit puts Proxima b inside what astronomers call the habitable zone, the range of distances where liquid water could theoretically exist on a rocky surface. Proxima Centauri is far smaller, far cooler, and far dimmer than our Sun, so its habitable zone sits much closer in than ours does. At 0.048 astronomical units from its star, Proxima b receives roughly the same energy flux that Earth receives from the Sun. On paper, the temperature works. On paper, you have a rocky world, slightly more massive than Earth, sitting in the right neighborhood around the nearest star in the sky. It reads like a headline you would want to be true. The complications, though, start almost immediately. Proxima Centauri is a red dwarf, and red dwarfs are not gentle hosts. They are magnetically violent, particularly when young, and Proxima is no exception. It is classified as a flare star, meaning it regularly produces intense bursts of X-ray and ultraviolet radiation that dwarf anything our Sun generates on its worst days. These flares are not occasional events. They are frequent and powerful enough that researchers modelling the environment around Proxima b have raised serious doubts about whether any atmosphere could survive long-term exposure to them. Charged particles, extreme ultraviolet radiation, X-ray pulses, these are the things that strip atmospheres from close-in planets. Earth's magnetic field and the relatively calm behavior of our Sun protect us. Whether Proxima b has either of those advantages is unknown. Then there is the tidal locking problem. At 11.2 days per orbit, Proxima b is so close to its star that gravitational forces almost certainly locked its rotation long ago. This means one face of the planet perpetually points toward Proxima Centauri, baking in permanent noon. The other face stares into permanent darkness and cold. This is not how Earth works, and the consequences for climate and habitability are profound. Any atmosphere thin enough to allow liquid water on the day side might freeze solid on the night side, collapsing and depositing itself as ice. A thick atmosphere could redistribute heat more evenly, but whether such an atmosphere exists, or ever existed, is something we simply do not know. No telescope currently operating can directly detect Proxima b's atmosphere. The planet does not transit its star from Earth's viewing angle, which rules out the transmission spectroscopy that has given us atmospheric data on other exoplanets. What we have is the radial velocity signal, a wobble in the star's spectrum, and the inferences we can draw from it. The radial velocity method gives a minimum mass, not a definitive one, because the inclination of the orbit is unknown. Proxima b could be more massive than the minimum figure suggests. Or it could be close to that floor. Without a transit, the radius is unknown, the density is unknown, and whether the planet is rocky at all is technically unconfirmed. Researchers have built climate models for Proxima b. Some of them are optimistic. A thick enough atmosphere with the right composition could maintain stable surface temperatures on the day side. Ocean heat transport could carry warmth toward the night side. There are scenarios in the literature where Proxima b is genuinely habitable, but those scenarios require a set of conditions: a substantial atmosphere, a protective magnetic field, the right atmospheric chemistry, survival through the star's early violent phase, that have to all be true simultaneously. Remove any one of them and the picture changes. The flaring alone may have eroded whatever atmosphere Proxima b once had before the planet ever had a chance to cool into something hospitable. What makes Proxima b frustrating is how close it is. At 4.2 light-years, it is near enough that next-generation telescopes and proposed interstellar missions have specifically cited it as a target. The Breakthrough Starshot Initiative has discussed sending light-propelled probes in its direction. The extremely large telescope, when operational, may be able to attempt direct imaging of the system. The planet is close enough to study in ways that planets around most other stars are not. And yet, for now, it sits just beyond the threshold of what we can actually characterize. We know it is there. We know roughly how massive it is. We know where it orbits. Everything that would tell us whether it matters. The atmosphere, the surface, the magnetic environment remains out of reach. The contrast with TRAPPIST-1 is instructive. Those 7 planets are 40 light-years away, but their transits gave us densities, mass estimates, and the beginnings of atmospheric constraints. Proxima b is 10 times closer, and we know less about it in the ways that count. Distance alone does not determine how much we can learn. Geometry matters. Orbital inclination matters. Whether a planet happens to cross its star from our line of sight matters enormously. Proxima b did not cooperate on that front, and so the nearest super-Earth remains one of the most tantalizing and least understood objects in the exoplanet catalogue. Proxima b is the closest super-Earth we know of, and we understand almost nothing about it that matters, which is a reasonable summary of where we are with super-Earths in general. There is a version of this story where not having super-Earths is not a neutral fact about our solar system, but actually a disadvantage. That idea runs against every instinct we have. Earth is the only world we know of that has life. It seems like the obvious template, the baseline, the thing to compare everything else against. But some researchers have started asking a different question. What if Earth is not actually the best planet the universe knows how to make? What if a world somewhat larger, somewhat heavier, somewhat more geologically active would be a better home for life than the one we happen to live on? The concept has a name. Scientists call it superhabitability, and it is exactly as provocative as it sounds. The basic argument is straightforward. A rocky planet, roughly 1.5 to 2 times Earth's mass, would have stronger surface gravity. Stronger gravity holds an atmosphere more tightly against the planet. Lighter gases, including the kinds that get stripped by stellar radiation or leak gradually into space, would be retained for longer. Earth has lost substantial amounts of hydrogen from its upper atmosphere over its history. A more massive world holds on harder. Over billions of years, that difference compounds. A super-Earth might maintain a thicker, more protective atmosphere across a longer stretch of time than Earth could manage at its mass. There is a second mechanism, and it might be even more important. Larger rocky planets contain more radioactive material in their interiors simply because they are bigger. Radioactive decay produces heat. That heat is what drives plate tectonics, the slow churning of a planet's crust that builds mountains, recycles carbon, regulates the long-term climate, and almost certainly played a role in making Earth habitable in the first place. On Earth, geologists estimate that plate tectonics will continue for perhaps another billion years or so before the interior cools enough to shut down. On a planet 1.5 times Earth's mass, that engine could keep running for several billion years longer. More geological time means more opportunity for chemistry, more carbon recycling, more stable long-term climate regulation. The surface area argument is also real. A planet 1.5 times Earth's radius has considerably more surface than Earth does. More surface means more coastlines, more shallow water environments, more interfaces between land and sea. Life on Earth is disproportionately concentrated at those interfaces. More of them, spread across a larger world, could mean more ecological niches, more biological complexity, more total biomass. These are not trivial advantages. Researchers who have worked through this framework, most notably Dirk Schulze-Makuch and René Heller, who published a formal study ranking potentially superhabitable exoplanets, suggest that the optimal rocky planet for life might weigh somewhere between 1.5 and 2 Earth masses, not dramatically larger, not approaching the 10 Earth mass upper boundary where you start getting into a different category of planet entirely. Just enough bigger to retain more atmosphere, run tectonics longer, and offer more surface diversity. Then the complications begin. Planetary science is rarely this clean. The same size advantage that makes a super-Earth more geologically active also makes it harder to reach space from. Surface gravity on a 1.5 Earth mass planet would be roughly 25 to 30% stronger than on Earth. That does not make the surface uninhabitable. It does not even mean life couldn't evolve there, but it changes the physics of every organism that develops. Bones and muscles built for that gravity would look different. Tall trees would face structural limits that shorter ones wouldn't. The biosphere would not be a simple scaled-up version of ours. It would be shaped differently by gravity from the cellular level upward. More critically, there is a threshold problem. Once you push a rocky planet above roughly 2 to 2.5 Earth masses, you enter a regime where the planet is massive enough to hold on to enormous quantities of hydrogen during formation. Hydrogen is the most abundant element in the universe, and it is everywhere in a young protoplanetary disk. A planet massive enough to gravitationally capture and retain primordial hydrogen can end up with an atmosphere hundreds of kilometers deep, crushing surface pressure, and no dry land at all. Some super-Earths we have observed may be exactly this, what astronomers call water worlds or hydrogen-shrouded worlds, where the surface conditions are nothing like what biology as we understand it could work with. The dividing line between a super-Earth that is more habitable than Earth and one that is completely smothered under its own atmosphere is not precisely known. It probably depends on where the planet forms in its disk, how much hydrogen was available, how intense the radiation from the host star was during the planet's early life, and how quickly the disk dispersed. All of those variables differ from system to system. This is part of why the superhabitability concept is still contested. The idea is physically motivated, but the boundary conditions are poorly constrained. There is also the question of what we even mean by habitable. If we mean habitable for something like us, the calculus is narrow. If we mean habitable for life in general, the range opens up considerably. Microbial life on Earth survives in conditions that would kill a human within seconds: boiling acidic springs, the interior of nuclear reactors, the dry valleys of Antarctica. Life is more resilient than any single world requires it to be. A super-Earth with twice Earth's surface pressure and 1.3 times the gravity might be hostile to mammals and hospitable to things we have not imagined yet. What this means, at minimum, is that Earth is not obviously the gold standard. It is the standard we know. That is a very different thing. The universe may have been churning out planets that are better candidates for life than Earth all along, and our perspective has been limited by the fact that we have only ever seen one example up close. The same events that prevented super-Earths from forming in our solar system may have made Earth possible in the first place. That is a strange thing to sit with. Everything discussed about Jupiter's early formation, the Grand Tack, the Pebble barrier, the depletion of the inner disk, all of it sounds like a story about what we lost, worlds we never got, planets that are common everywhere else and absent here. But there is another way to read that same chain of events, and it leads somewhere unexpected. Jupiter is enormous. It contains more mass than all the other planets in the solar system combined, and it orbits close enough to the inner system that its gravity reaches everything. One of the things astronomers have debated for decades is what that gravity actually does to the stability of the inner planets. The traditional view, repeated in science documentaries since the 1990s, was that Jupiter acts as a shield. The idea was straightforward. Jupiter's gravity deflects incoming comets and asteroids, pulling them out of trajectories that would otherwise send them crashing into Earth. Without Jupiter, the argument went, our planet would be hit far more often, and life would struggle to get a foothold. The reality, as it turns out, is messier than that. Jupiter deflects some objects inward as well as outward. It sends certain comets toward the inner system that might not have arrived otherwise. The shield picture is not quite right, but there is a version of Jupiter's protective role that does hold up. The same migration history that sculpted the inner solar system, the inward plunge, the sweep through the asteroid belt, the reversal, the outward drift, left the inner region in a specific state, depleted, low mass, dynamically quiet. The asteroid belt today is a shadow of what it once was, containing less than 4% of the mass it likely held before Jupiter's passage. That sounds catastrophic. In one sense it was, but a thin asteroid belt is also a belt that delivers fewer large impactors to Earth over long timescales. The bombardment Earth has experienced since life began, while substantial, may be modest compared to what would have occurred if the asteroid belt had retained its original mass. Now consider what would have happened if the Grand Tack never occurred, or if Jupiter formed later, or never reached its full mass before the disk dissipated. The inner solar system in that scenario likely follows the pattern seen everywhere else. Super-Earths form. They migrate inward. They pile up inside one AU in chains of orbital resonance, several of them packed into the region where today only Mercury, Venus, Earth, and Mars reside. What does that do to Earth? The answer is probably nothing good. A planet of 5 or 6 Earth masses sitting at 0.7 AU, right where Venus orbits today, does not leave Earth's orbit alone. Massive close neighbours are gravitationally disruptive. They perturb nearby orbits over time, introducing eccentricity, pulling planets out of stable circular paths, sometimes ejecting smaller worlds entirely. The very tight spacing of observed super-Earth systems works in those systems because the planets form together in that configuration and settled into resonance chains that are self-stabilizing. Drop a super-Earth into an inner solar system after the fact, or let one form while another planet is also trying to establish a stable orbit, and the outcome is frequently destructive. Simulations that add a super-Earth to the inner solar system's current architecture consistently show the terrestrial planets being destabilized. Earth's orbit, in many of those models, does not survive long. Orbital stability matters more than it might seem. Life on Earth required not just liquid water, but liquid water for billions of years. Complex life did not appear overnight. The fossil record shows simple microbial life appearing within the first billion years, but the kind of multicellular complexity that eventually led to animals, to forests, to everything recognizable took far longer. 4 billion years of relative stability, an orbit that stayed roughly circular, seasons that were predictable enough for ecosystems to adapt to over millions of years. A slight increase in orbital eccentricity, the kind a massive inner neighbor could easily introduce, changes the range of temperatures a planet experiences across a year. Push that eccentricity high enough, and the climate swings become catastrophic. There is also the question of the Moon. Earth's large moon is the result of a collision early in the solar system's history, when an object roughly the size of Mars hit the young Earth. That collision, as destructive as it was, produced a moon massive enough to stabilize Earth's axial tilt over long periods. Without the moon's gravitational influence, Earth's tilt would wander chaotically, driven by the gravitational pulls of the other planets. That wandering tilt would mean extreme climate shifts, poles pointing directly at the sun for extended periods, tropics plunging into darkness. Complex life finding stable footing in that environment seems unlikely. A crowded inner solar system packed with super-Earths makes that kind of stabilizing collision less probable, not more. More bodies competing for the same space means a more chaotic early history, more ejections, more collisions that don't produce useful outcomes. None of this is to say that life requires a solar system exactly like ours. The universe keeps surprising people who make confident claims about what life requires, but it does suggest that the specific emptiness of our inner solar system is not a neutral fact. It is a condition, one that gave a small rocky planet at 1 AU the time and stability to develop something worth talking about. The architecture of our solar system, the emptiness of the inner region, the dominance of Jupiter, the oddly low-mass rocky planets, may not be a random quirk but a specific configuration that had to be in place for a planet like Earth to remain stable long enough for complex life to develop. The question of whether our solar system is typical or exceptional used to be a philosophical one because we had no other systems to compare it to. For most of human history, we had one data point, one sun, 8 planets, one arrangement of rocky worlds close in, and gas giants farther out. That was the template. It was the only template. Then the exoplanet surveys came in and rewrote everything, and what they revealed was not a galaxy full of solar systems that look like ours. It was a galaxy full of systems that look almost nothing like ours. The evidence is now substantial enough that the question is not really whether our solar system is unusual. It is. The more interesting question is how unusual, and whether that unusualness was the point. Look at the numbers in order. Super-Earths appear around more than half of all sun-like stars. Around red dwarf stars, the rate climbs even higher. The Kepler data showed that roughly 77% of Sun-like stars host planets in the super-Earth size range with orbital periods under 300 days. Our Sun hosts 0. Our inner solar system, the region inside roughly 1 astronomical unit, contains 4 rocky planets, with a combined mass well below that of a single typical super-Earth found orbiting another star. By galactic standards, the inside of our solar system is nearly empty. The terrestrial planets we call home are not just smaller than super-Earths, they are small in a way that stands out. Mercury is less massive than some moons in the outer solar system. Mars is a stub of a planet. Even Earth, the heavyweight of the inner 4, would be considered a minor world by the standards of what Kepler found everywhere else. The combined mass of our 4 rocky planets is roughly 2 Earth masses. A mid-sized super-Earth in another system might carry that much mass in a single world. This is not a minor difference in degree. It is a structural departure from the galactic norm. Then there is Jupiter. Jupiter is part of what makes our system strange in a second way, distinct from the missing super-Earths. Gas giants on long, roughly circular orbits like Jupiter's are not common. Most stars that host giant planets host them on tight, eccentric orbits. Hot Jupiters that spiraled inward through the disk and settled close to their stars. Jupiter did something different. It formed fast, acted as a barrier to inward-flowing pebbles, possibly migrated inward and then reversed course, and ultimately ended up where it sits now, on a nearly circular orbit beyond the snow line. That particular biography is not the standard one. A Jupiter like ours, in an orbit like ours, appears around a small fraction of Sun-like stars. The combination of a mass-depleted inner system and a well-placed cold Jupiter on a stable orbit makes our solar system a fairly rare configuration by any honest accounting. Statistical surveys of nearby stars are beginning to put rough numbers on this. Systems that share the broad architecture of our solar system. No close-in super-Earths, giant planets on wide orbits, small rocky worlds inside, appear in perhaps 10 to 20% of observed systems at generous estimates. Some analyses put the fraction lower. No survey yet has a clean sample large enough to settle the number precisely, and detection biases still complicate things because the instruments that found most exoplanets were best at finding the close-in planets our system lacks. But even adjusting for those biases, systems like ours appear to be in the minority, not vanishingly rare, but not the default outcome either. Here is where the anthropic argument enters, and it is worth taking seriously before dismissing it. We are asking this question from Earth. Earth exists because a specific and improbable chain of events unfolded over billions of years, and part of that chain was the early formation of Jupiter and the Grand Tack, and the resulting depletion of the inner solar system. If those events had not occurred, Earth as we know it might not exist. So the fact that we find ourselves in an unusual solar system is not entirely surprising. Any observer capable of asking the question has to be in a system where the conditions for complex life were met. That requires a certain stability. That stability may require a Jupiter in the right place, and a Jupiter in the right place may require the unusual formation history that left our inner system empty of super-Earths. You cannot find yourself in the wrong kind of system. The wrong kind of system does not produce anyone to do the finding. The problem with anthropic reasoning is that it can explain almost anything without actually explaining anything. It tells you why you should not be shocked to find yourself in an unusual place. It does not tell you how unusual, or what the underlying physics was, or how often the galaxy reproduces these conditions elsewhere. It is a correct observation that functions as a near-perfect excuse for not going deeper. The physicists and planetary scientists working on this problem are not satisfied with it, and they are right not to be. The anthropic argument is a ceiling. It does not replace the need to understand the actual sequence of disk conditions, pebble fluxes, migration histories, and giant planet timings that produced our particular outcome. The honest picture at this point in the research is that our solar system formed through an unusual combination of circumstances. A disk that may have been structured differently than most, a Jupiter that formed quickly and then went on a specific migration history, and a set of dynamical events that cleared the inner region before super-Earths could take hold. Each of those factors alone might be moderately unlikely. Together they may be rare enough that our kind of solar system represents a real minority in the galaxy, though not an impossibly small one. The size of that minority matters enormously for how we think about planetary habitability, about where life might exist elsewhere, and about what kind of place Earth actually is in a broader cosmic context. We are not asking whether Earth is special. We already know it is, in the specific sense that it produced us. We are asking whether the solar system that made Earth possible is the kind of place the galaxy builds routinely, or the kind of place the galaxy built once and forgot how. The next decade of exoplanet science is going to give a much sharper answer to this question than anyone has been able to offer so far. The extremely large telescope, currently under construction in the Atacama Desert in Chile, will be nearly 40 meters across, large enough to collect light from the atmospheres of super-Earths orbiting nearby stars and break that light into spectra. Spectra tell you what molecules are present: water vapor, carbon dioxide, oxygen, methane. For the first time, it will be possible to look at a super-Earth a few dozen light-years away and ask not just whether it exists, but what it is made of, whether it has weather, whether something might be living on it. That is not a small step. That is the measurement planetary scientists have been waiting for since the first exoplanet survey came back and showed us what was out there. Space-based instruments are closing in from a different angle. Improved radial velocity surveys are being designed specifically to reduce the selection biases that have skewed the census toward close-in planets around small stars. The goal is a more complete map, one that captures super-Earths at wider orbits around a broader range of star types, including stars that look more like our own Sun. Every time the census gets more complete, the absence of super-Earths in our solar system becomes more precisely defined. Right now, the gap between our system and the galactic average is striking. With better data, researchers will be able to say exactly how unusual we are, whether the specific configuration of our solar system falls within any recognizable category of outcomes or sits entirely on its own. Theoretical models are keeping pace. The simulations that trace disk physics from the earliest dust aggregation through pebble accretion, migration, giant planet interference have grown dramatically more sophisticated in the last 10 years. Researchers are now running models that track not just where planets form, but how the pebble flux evolves over time. How Jupiter's early formation would have starved the inner disk at different rates depending on the disk's initial mass and structure. How the Grand Tack's specific migration path would have affected different populations of planetary embryos at different stages of growth. These are not simple calculations. Each one takes weeks of computing time. but the outputs are starting to converge on something that looks like a coherent story, one where our solar system is not inexplicable, just improbable, the result of several unusual conditions landing in the same place at the same time. What is harder to model is what it means. Billions of super-Earths are almost certainly out there right now, orbiting stars you can see on a clear night without a telescope. Planets larger than Earth, possibly rocky, possibly warm, possibly wet, in systems that formed the way most systems form rather than the way ours did. We cannot image them directly yet. We cannot read their atmospheres yet. We can only count them, estimate their properties from the way they tug at their stars or block their light, build the best theories we can about what they look like up close. Every star in the night sky that hosts a super-Earth we cannot see is a version of a question we are still learning to ask, and the fact that our own sun is the exception is the most interesting thing about it.